Welcome. Yeah. So this is going to be the first class in supervised learning for machine learning. So um, in the previous one, we got a quick introduction into um, machine learning generally as a subfield of data science, where we attempt to teach machines, computers, a way of learning and making decision without being explicitly programmed. And we talked about the fact that there are subfields in machine learning. So we have the classical machine learning, we have the deep learning, and there is the reinforcement learning also. Another classical machine learning, we talked about having supervised or unsupervised learning, and in there, we also mentioned the fact that under supervised learning, you can have two type of problems. You can have either classification problem or regression problem. So basically, the tree is going to look like this. So we're going to have machine learning. Let me paste that here. Make this smaller a bit. Machine learning or ML. Then under ML, we have a few bits. We have classical ML, and we have deep learning. And this is where we are actually going to be stepping into for the you know first few sessions in this particular series. So under classical ML, we also have supervised learning, supervised learning, and we have unsupervised learning. Great. So now under supervised learning, here we now have another subfield which depends on the kind of problem that we are solving. So first one is the regression algorithm or regression problems, and second one is the classification classification algorithms. All right. So in the class in this session today, we are really going to be looking at regression algorithms. So what's regression algorithms or what's regression problem under supervised learning? That is situation where your your target, what we want to predict. So what we want to predict as continuous value. So for example, let's say we are trying to model. We have a data set where we have x1 and x2, and we have some y that we want to predict. In that case, let's say we have 2, 3, 4, 1, 1, 2, 3, 5, and here we have 10, 17, 15, and 8. Now, in this case, if we want to use these x's, x1, x2, to predict this y, this is going to be a regression problem. Why? Because y here, the values of y here, they are continuous variables. Like they are variables, numeric variables that just can go on and on and on. So that's what makes it a regression problem that is going to require some regression modeling, some regression algorithm. But if this y had been some categorical variable, let's say yes, no, has cancer, does not have cancer, things like that, that's going to be a classification problem. So in this particular session, what we are going to be looking at is the first regression algorithm, which is like the absolute basics, which is linear regression. So in this session, we're going to be looking at linear regression, linear regression, linear regression. So I like to think of it as the most fundamental, the most basic regression algorithm. Now, for this particular course, we are really going to be working on collab. So if you don't have a setup, you probably should do that. And I think that you don't really have much to do because once you have a Google account, as long as you have a Google account, that comes with collab. Just go to this link, collab.research.google.com. And everything I'm trying to do is to make sure that you can always reproduce everything we cover in this session. Like if we cover something, it is easy for you to reproduce it because certain environment can be a bit tricky, especially if you're just starting out. And considering the fact that majority of people that are going to be watching this video or following this course are on Windows, and Windows can be a little pain to set up for development. But we'll get to that part. Once we get to the model deployment part of ML, you are going to really get to the part where we have to work on things like VS Code. And another thing is when we get to deep learning, Colab actually gives you GPU to use for free, although it is metered, but it's for free. And that's something you probably do not have with on your current computer. Right. So, but the main reason why we are using Colab is for reproducibility. So now let's get into once you have this setup, let's go back into the part where we explain this. So what's linear regression? So linear regression is actually an algorithm, a technique for making prediction, and it comes really from it is very very old. It is older than machine learning itself. So I think it's from statistics, from maths generally. So and the idea is that if we have some variables that exhibit linear relationship, then we can model it. And what does that mean? So here's the thing. The belief in maths, which is actually I think proven, is that the relationship between if we have some variables like we do x1, x2 here and y, the relationship, if we want to actually write the equation of this relationship here, this particular relationship, that is going to be y equals, that is this y here equals, and that's going to be beta naught plus beta 1 x1, which is this x1 here, plus beta 2 x2 plus e, like this. And this e is called the residual. This e here is called the residual. So if I want to, or the error term, if I want to annotate this, so this e is going to be the residual, and this beta naught, beta 1, I'm sorry, beta 1, beta 2, beta 1, this is beta 2, right? And this is supposed to be beta 1. So this beta 1, 2. They are both weight. And this one here is going to be the bias, right? So, and what does that mean? That means that for us to actually get the solution of this y here, for us to be able to model this y, that is use these two x's to predict this y, the relationship that exists between them is that if you take some beta naught, which is the bias, add it to the product of a weight corresponding with this x1, another weight corresponding with this x2, plus some residual, some error time that we cannot model, then what you are going to have at the end of the day is you are going to have this particular y here. Don't forget I mentioned that this residual is another name for it is noise. We really cannot model it. So what that means is that for us to actually learn the things that leads to us predicting y. So that if we have a new record here, if we have a new information here, we can always just um, take our algorithm that we've put together to predict it. So for us to be able to learn that, what we need to do is just solve this particular equation to return beta naught, because look at it, we already have x1, we have x2, x1, x2, and we already have y2. So what we need to solve for is beta naught, beta 1, and beta 2. And we are going to have some solution that takes us to this close value, and we are only going to be wrong or off by a value of this residual that we really cannot model. So where does that bring us? That brings us to um, the equation of our y predicted. So this is, you can think of this as y true. This one here, and call it y true. So we can say y true equals this. So what is y predicted going to be? So we're going to say y predicted, that is the y that our model is going to be predicting, is going to be equals to beta naught plus beta 1 x1 plus beta 2 x2, and that is it. And you're going to see that the only difference is there is no residual here. That is, this residual here, we cannot model it. We cannot actually have, we don't have a way for us to capture it in our prediction because it changes. It's noise. It's just some tiny little factor that we cannot add to this. And what you see here is what linear regression attempts to help us solve. Now, how does it do that? So we are going to be using the library called Sklearn, but what does it do under the hood? So what Sklearn does under the hood is to actually find some values of beta. Let me show you this. We are- excuse me, some values of beta here. Let's call it cap like this. And what we are trying to do is we are trying to minimize. If you actually check Sklearn documentation, you are going to find it there. So we are trying to say we are finding, excuse me, finding the, we are trying to minimize this particular relationship here, which is going to be the x that we have, this x here, x1, x2, this one here, all of our x's, multiplied by beta, sorry, x multiplied by beta minus y, like this. And you know, it is possible that we get into negatives, right? So we square it all up. Now, what does that mean? That means that one, the two things that we can take away from this is number one, we know for a fact that a regression problem is a minimization problem. And what are we trying to minimize? We are trying to minimize our loss. And you get to that part, we'll get to that part shortly. But the true thing is, how does this thing get solved? The way it gets solved is, although there are a lot of techniques inside SQL, but the popular one that comes from, stats generally is something called OLS, ordinary least square method. And what is that? The way that works is this. It says that all of our beta, which in this case is beta naught, beta 1, and beta 2. So we can say our betas is going to be equals to, can say x transpose x inverse. Sorry, where am I? Okay. I think connection is okay. Fine. So x transpose x inverse multiplied by x transpose y. And the solution of this particular equation, if you solve this particular equation, it is going to give you the perfect value for our betas. So what does that mean? If we take, because this can actually be represented as a matrix, this one here, this particular one here can be represented as a matrix. In fact, it is a matrix form. So we can have a 2 by 4 matrix, that is 2 rows, 2, 1, 3, 2, 4, 3, 1, 8. Now, that's going to be our x's, and this is going to be our y, 10, 17, 15, 8. And if we solve that, If we pass that into this place and we use it to solve this particular equation, we are going to have a matrix as our output, which is going to be a matrix that correlates that corresponds with beta naught, values of beta naught, beta 1, and beta 2 that we can plug into this equation, and it's going to give us our y predicted every time. Cool. Now, once we have that, once we have that solved, it means we can take random values or new values, can take new entries, pass it into this equation here, and it is going to return us a value that we can compare with the true value if we have true values at hand, and see how the model has performed. And model performance is going to be what? The difference between y true and y predicted, which in reality is just going to be residual, what we could not predict, right? And the whole idea is this. The whole idea is that there is a linear relationship, right? That is, let's say this thing is just a chart of x and y. So let's say we only have x and y, and this is our x-axis, and this is our y-axis. So what we are saying is this. Let's say for when x equals, let's say this is 1, 2, 3, and this is 2, 4, 6, something like that. So if we have one here, I have another here, I have another here, I have one here again, I have one here, and let's say one here. Now, what we are actually looking to do is to draw a line that is what this equation, let me show you this equation. What this equation is looking to do, this one here, is to draw a line that fits this relationship best. And that line is going to be the line that minimizes the most error. So if we are drawn something like this, if we draw something like if I draw something like this, let's say I draw something like this. Now, then I have another line, let's say another one like this. Right. Now, which one is the best line? The best line that is going to give us the least error is this green line, because it captures most of the values here and only misses these two, which is going to be the error term here. And if we had gone with this line, it is going to miss about, I don't know, that's about four, even one, two, three, four. Yeah, four. So it's going to miss four lines. So this equation is actually helping us to get the line of best fit by finding the optimal bias and weights that if we plug our values from the data set into it, gives us some new subsequent y. And what we now do is, after getting our y predicted, we can now evaluate the model, see how the model has performed. And how can we do that? The way to do that is the way to evaluate our model is by using something. There are a lot of things, but one that we can use is RMSE, which is root mean squared error. And what is root mean squared error? Root mean squared error is the metric that we use to actually evaluate how a regression model is performing. So imagine here, we've gotten our y. Let's call this one y true. That is the true y that happened. So let's say the model has finished evaluating, and now we have y predicted. So let's call it y preds. So let's say at this point it predicted 8. At this point it predicted 19. At this point it predicted um let's say 5. Then let's say maybe this is going to be 2. This is going to be minus 2, that is 0. This is going to be 10, and 15 minus 5 is 10. So let's turn this one, instead of making this one 8, let's make this one 25. and we can make this 15. Perfect. So now let's say this is the prediction that the model has made. After we've trained it, it has made this prediction. We need to know how it is performing. And how can we know that? A very simple thing that you can actually do is just subtract. What do you expect? What actually happened? What's the true value? 10. What did the model return? It returned 8. 10 minus 8, that is going to give you 2. 17 minus 19, that's going to be minus 2. 15 minus 5, that is going to be 10. 25 minus 15. Okay, that is not what I was gunning for. What I'm gunning for is for this to be 15 and this should be 25. It should be 25. So 15 minus 25 is going to be minus 10. Now imagine the next thing that we do is we add up all of the errors and divide it by 4. The way you compute averages. So this is going to be 2 minus 2. That's 0. Plus 10 minus 10, that's also 0. So it means that at the end of the day, you have RMSE of 0. So what does that mean? You have an average error rate of 0, meaning that what? On average, this particular model is not making any error. But that's wrong. Why is that wrong? Because you see here that it made an error here. It is off by 2 units here. It is also off by 2 units here. Also off by 10 units here, 10 units here. So, but the reason why it looks like this is because, well, this is negative, this is positive. So things are beginning to cancel each other out. So what do we do to avoid that? We square this difference. So we call it diff. We square it. So if we square it, it removes that problem. So that means this is going to become 4. This is going to become 4. It's going to become 100. This is also going to become 100, regardless of the value. So if we add all of this together, 4 plus 4, 8, that is 208. 208. Then we can now have 208 divided by 4 and we root it. And this value is going to be what gives us the true error rate. So, and that is what we call the RMSE that we are finding here. And the formula for that is the RMSE is equal to the root of y minus, which is basically, you can think of it as y true minus y pred, or however you want to put it. Excuse me, there should be summation because we added things together. So that's going to be summation of y minus y hat all squared all over n, number of observation that we have. So what does that mean? It means the exact thing that we've computed here. So we take each of our prediction, each of our true values, subtract from the prediction, we square it, add all of them together, and divide by n, and that gives us the true error that the model is making, plus or minus. So yeah, that is all of the basic fundamental idea behind linear regression that you need to understand. So we are still going to be revisiting this page, but let's get into the part where we code it up. So we are going to be using, for majority of the things that we have in here, we are going to be using Sklearn to do it. So Sklearn is a library that contains a lot of things that you would need to do classical machine learning. So let's rename this, name it linear regression. So we are going to just hit connect here. So I'm going to say, so the first thing I want to do is we want to um I want to load the libraries and data set. The libraries that we're going to be needing, we're going to say import pandas as PD, import numpy from the classes that we had on EDA, on exploratory data analysis. You already know what all of this library does, pandas and numpy. Then we're going to say from sklearn, which is the library that we're going to be using, dot linear model, we're going to import linear regression like that. Then another thing that we're going to be needing is we are going to be needing um say maybe plotly. We're going to from we're going to import plotly dot express as px. Now we are just going to run this. Now you might be wondering, well, why did we not import cborn and matplotlib? That is because this is not the class for, I don't want this lesson to be too long. So this is not the class for exploratory data analysis and visualization. They are already, there's already a playlist on that you can go through and learn how to do a lot of EDA. And the fact that this session, this lesson is, and the subsequent ones are going to be completely focused on the ML part does not mean on the job that is the way it works. No, on the job, majority of the effort goes into exploratory data analysis. So always be mindful of that. The reason why we are not doing a lot, that we are not going to be doing a lot of EDA in this particular session is because we want the video to be as small as short as possible and for the focus to be on ML, right? Which is what you are here to learn. So that's the reason. Now, the next thing we're going to do is load our data set. Now, normally your data set is going to come from somewhere, let's say a database, web scraping, anything. But for ease of reproducibility, so that you can access this course and get good value from it without having to download a lot of things, we are going to be using some practice data set from Plotly. I'm going to say import practice dataset from Plotly. So we are going to say that um, data is going to be equals to px. So inside Plotly, there are a lot of um, practice dataset there. There's a px.data.tips. There is a tips dataset. So there's a data.ed. So if you run that, we have this practice, this tips data set here, this one. Normally, again, I need to reiterate this, especially if you are not very solid with all of this. Normally, if you have a data that you want to use, your own data, and you want to use it in Collab, you click on this place, you upload the data to session storage, and you come here and type data equals pd.read.csv, the way you do things normally. But if I should do that in this case here, it will mean maybe on the description I have to now send a path to the data set. Let's say the data is on cargo and you have to download and all of that. But to save time, that's why I'm using the practice data set. Good. So next thing we're going to do is we are going to actually do a bit of cleaning. And why do we need to do a bit of cleaning? Uh, all of these categorical variables, sex, smoker, day, and time, they need to be converted to numbers, to numeric form, so that we can use them to predict, so that the computer can understand it. So computer does not understand text as they are. Now, but the first thing we need to understand is what are our x's, like we showed here. What are our x's and what is our y? So our x's in this case is total bill, sex, smoker, day, time, size. And what we want to predict is tip. So our y is tip. Good. So it means we want to use total bill. You can think of this data set like a restaurant data set. And they are saying, okay, we have you as a machine learning engineer and or a data scientist, and we want to actually have a system where we can predict how much somebody is going to tip based on what they spent, their total bill, their gender, whether they smoke or not, the day they came in, the time they came in, whether they came in for lunch, dinner, or breakfast, and the size of the table they ordered. So we want to use that beforehand to know what they're going to tip. All right. Tipping is a big culture in the United States, right? So that there is not going to be issues. We can have expectations along the lines of what they are going to tip. So now yeah, that's what we're going to do. So let's just do some data wrangling. So I'm going to come here and add Where are you? Perfect. Data wrangling, just a little bit of it. And in real life, you are going to do a lot of it, like a whole lot of it, right? But and data wrangling is part of exploratory data analysis. Cool. So the first wrangling that we are going to do is turn female sex, smoker, day and time, turn it to categorical variables. And how are we going to do that? We are going to do it with, I mean, you could do it with something like list comprehension. If you don't know what list comprehension is, you need to revert back to Python basics. There's a playlist on this channel also on Python basics on that. So, but what we are going to use is we are going to be using a library called we are going to be using a module from Sklearn called label encoder. So I can say from Sklearn dot preprocessing import labeling, not label binarizer, label encoder, right? And yeah, I'm going to rerun this line again and come here to encode. So I'm going to say encode the categorical variables. So the first thing we're going to do is we're going to actually get out the categorical variable. So we can say data dot select underscore the types, and we are going to say include. We only want it to select things of type object. If I should run this, it's going to return column of type object. Can you see? These are the only columns that are of type object, sex, smoker, daytime. So what we are going to do is we are going to call dot columns so that I return the column names. Do dot columns. We have these column names and we can list it if we want or not. I can list that and it becomes an actual Python list. Then I can call that cat underscore calls, or let's call it categorical calls, and like this. So we can loop through that. We can say for column in categorical underscore calls. So what we are going to do is we are going to start encoding each one after the other, one after the other. So we are going to say we are going to initialize the encoder. We're going to say encoder equals that stuff that we wanted to use earlier. So, from object-oriented programming, if this is a class, right? And for you to be able to create an object of a particular class, the first thing you do is you initialize it. You have to do that thing equals an instance of you create an instance of that class. So that's what we are doing here. We are initializing init the encoder, right? So the next thing that we're going to now do is we are going to say data of that column, which when it starts is going to be sex. It's going to be data of sex, that is the new sex column, is going to be encoder dot fit underscore transform, and that is going to be data of column. Now, one thing that is very important for us to understand is any pre-processing that we do, when we get to the point where we want to use this thing to make prediction, any pre-processing that we do, we must actually revert the pre-processing. We must we must also do that pre-processing. So it might make sense for you to track all of the encoding that you do, because encoding is a column by column thing. Let me show you this. I'm actually going to practicalize it for you. So if we do encoder.fit transform, then we check data now. So if we say data.add now, so if you run this now, you're going to see that sex, smoker, daytime, and size, they've been encoded. Sex is zeros and ones because it's just male, female. Smoker is yes or no. So that also is going to be zeros and one. But I think all of the first classes, they are all the same value. And they are all no, 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 no. Then day also is going to be some things, but the first ones are also going to be the same value. S- Sunday, 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 Sunday. So Sunday means two. Then time also, the first ones are dinner. Then we didn't touch size. Now, if I come here and I want to get back the value of time like this, I can say encoder dot inverse transform. If I should pass in um time there, and I say data of time, that's me wanting to get back what was inside time. That has to be in quotes because it's a colon. Now you're going to see that it says dinner, dinner, lunch. This is how we encoded these guys, right? So you see what I mean? Like this is dinner, lunch. So we've converted data time from just 00012 to the stuff back. But if we try to do it for which one? Day, it is not going to work. If we say day, you're going to see some. Can you see? It is not going to work. It says Y contains previously unseen labels 2 and 3. And the reason is because encoding is a column by column thing process. So it means that in this for loop, the first thing we did was we encoded sex. Then when the loop finished, we went back up, encoded smoker, went back up, you reinitialize this, went back up. Every time we reinitialize, it forgets what it did inside sex, moved on to smoker, move on to day, forgot what happened in smoker, moved on to time, forgot what happened in day. So that's the reason why the last one that worked was time. So to save that, we can just grab an empty dictionary and call it label underscore encoders. So what we are going to do is for everyone that we do, once we are done, we're just going to say label. If you don't know how dictionary works, also you should refresh your basics. That is going to be extremely beneficial. So we're just going to update this dictionary with an instance of our encoder every single time. So I need to come back to this place, rerun this data so that we have uh, a fresh new data again. Then if I run this now, this still works. Is that right? But now, what I can now do is, if I want to make this work now, I can actually say label encoders of day like this. If I do inverse transform day, now it is working. We have the one for day, which is Sunday, Thursday. If I want the one for time, I want it to reverse it back. And I come here and I put time here and I run that. That is going to return for time. And if I want for sex, if I want to do it for sex, I do sex, oops, sex like this, and I run it. That's going to give us for sex. Great. So that is what I wanted to show you. So our encoding is done, and we also have the ability to reverse it if we want. So the next thing we're going to now do is we must get to the modeling part now so that we don't this thing does not get too long. Now, in the modeling part, what do we need to do? What we firstly need to do is separate our x and our y. So we're going to say um, separate the x and y. That is the features and the target and the label. So our x, which is capital X, meaning signifying that there are several x's, which correlates with what you have here, x1, x2, up to any number of x that we have. So that is going to be all of the things that we want to use to predict. So it means we need to remove tip, which is what we want to predict. So I'm going to say data.drop and columns is going to be equals to tip, and our y is going to be equals to data tip. Great. The second thing that we need to do is we need to split our data set into train and test set. So what does that mean? That means that you can imagine, you can think of it like this. You are trying to teach some students how to do something. Let's say you're trying to teach them, you're a math teacher, right? You're teaching them mathematics. For you to actually know whether your students are good, whether they are intelligent and they are really understanding what you are teaching, you teach them. Let's say you have 10 questions in total. You teach them with about, let's say, 7 questions, and you now give them some exercise with 3 questions that they have not seen, which relates to what you've taught them. But imagine you taught them with all of the 10 examples and still proceeds to remove out of the example to now explain things to now evaluate them. You know, even if they do well, you are not going to be confident very much, because you don't know whether what they did is memorize the solution, or whether they are actually good enough. Do you understand? So that's the idea behind splitting our data into train and test. So we're going to train the model with some chunk of data, and we're now going to test the ability of the model. So in the case of this one here, we can train the model with these first three rows, here. Then we can now test it with this one. Perfect. So how does that work? We're going to come here and back to the top here. We are going to say from sklearn dot model selection. We have another thing called train test split that we can use to do that. So Sklearn is a very cool library. It contains majority of the things you need to get your job done. So we're going to say X. If we just come and say train underscore test, train test split, the first value that goes in is the X, which is all of our X's. The second one is our Y, and the next one is our test size. What is the size of the test that what is the value that you want to keep? What is the proportion or the percentage of the data set that you want to keep for testing? So in this case, I can say 0.25, that is keep 25%. Then I can add random state. Random state is, I can say 23. So what does random state do? Random state is our way for labeling uh, a particular random operation. What does that mean? The way this guy is going to split this thing, the way the train test split is going to split this data, it is not going to take the first 75% as train, then the last 25% as test. It is going to randomly select. It can actually select, in fact, it can select 0 into the train, put 1 into the test. Now imagine you do this and you get some results. Maybe you get home or you get to your superiors and you want to repeat this particular experiment, and you begin to get a different result just because you didn't track the way you split the data. So that is going to be a problem. So that is where random state comes in, a way for you to reproduce an experiment. Anything that is random in machine learning is going to have some way for us to set a seed that controls the randomness. So you could use any value here. Just make sure that whatever value you use, every time you want to get the same result, you have to use that exact same value again. So if we run this, can you see the outcome now? So the outcome is actually a list. And in that list, the first thing we have is this particular one, which is our train set. Then we have another one, which is our test set, our X test. And we now have another one, which is our uh, Y train, this one. Then we now have another one, which is our Y test. For example, it actually puts 183 rows and 6 columns inside the X train, 61 rows and 6 columns inside the X test. Then the next one is this 183 rows, no column for the Y train, and the last one 61 rows, no columns for the X test. So we are actually going to unpack this. So we're going to say x underscore train, comma x underscore test. If you don't know what unpacking is, you should also review the basics. Y train, y test. So that's going to be equals to this, and we can maybe take this to the next line. So if we run this now, everything is fine, right? Everything is fine. Or we can control X this and say split output. We can call this split underscore output. That is the output of the split. And I can backspace this. Now, we can also say, we can check how the split has happened. We can say for split in split underscore output, we can do split dot shape. We can print, I'm sorry. Yeah, F string, that's correct. Split, or maybe not F string because we are not adding any variable there. So now can you see? So this is our X string. This is the shape of the X string. This is the shape of the X test, Y train, and Y test. Cool. So the next thing that we can now do is we can actually unpack everything. So we can say, or maybe just do that at the top here. Or not. Excuse me. We can do that here and say um X train X test, Y train Y test is going to be equals to split underscore output. Great. So the next thing for us to now do is model training. So we have our X train X test, Y train Y test. So the next thing to just do is proceed to training the model, and that is the easy part. The model training. Now, cool. So excuse me, we did not label that. Let's just say model training. All right. So the next we want to do is we want to take this particular formula here, this particular equation here, exact it on our data set and use it to get the weights that we can use to make predictions. So how is that going to work? The first thing is we initialize the model. I'm going to say model equals linear regression, and that is everything we're going to do. And after that, let me actually even put it in front of it here. So the next thing that we do after that is we fit the data to the model. So I'm going to say model dot fit X train, comma Y train. Fit the data to the model. Then the next thing to do is to actually get our train and test predictions. So I'm going to say train underscore preds. It's going to be equals to model dot predict X train, and test underscore preds. It's going to be equals to model dot predict X test. Right, and that is everything. But let's just have comment here. Say get train prediction. Here we get test predictions, and that is that. Now the last thing that we are now going to do in the aspect of model training here is to evaluate performance. So we're going to say evaluate model performance. We want to see how the model has performance, which is which one again? Which is this one here, this RMS here. We want to act, we've gotten these values here, these Y preds for both the train and the test. So what we now want to do is we want to get RMSE. How has the model performed? So we are going to say, we are going to go up again. There's a library for doing that also, which is the RMSE. So we say from Sklearn dot metrics. So majority of the things you are going to need, they are all in Sklearn. So from Sklearn dot metrics, import root mean squared error. And we can come all the way down here and say train underscore RMSC is equals to root mean squared error. And the first thing it takes is the y true, what actually happened. So that's going to be y train, comma, what the model predicted. Then, excuse me, then for test RMSC, that is also going to be root mean squared error of y test, comma, test prets. Great. So we can print out these two things. So we can print f string train RMSC, that is going to be equals to train RMSC, and test RMSC is going to be equals to test RMSC, and that's going to be test underscore RMSC. So if we run that, we have this output, and it says that train RMSC is 1.03, test RMSC is 0.95. So it means the tips that we are predicting, these tips that we are predicting here on the train set, the model is making error of 1.03, while on the test set is making error of 0.95. Meaning that, like I mentioned at the start of the lesson, RMSC regression is actually a minimization problem. Our goal is to minimize the RMSC, and the RMSC is much more minimal in the test set, meaning the model has performed better on the test set than the train set test. At least in this case, there is no overfitting. But don't worry, in the subsequent class, you are going to understand better what overfitting and underfitting means. Great. So what we are now going to do here is we can actually try and spin up a function that can now make prediction. That is, we already have something to help us make prediction, right? So why not try and see if we can actually set up a function that is going to that is capable of making prediction. So what are the things that we need at the top here? So we need total bill. In fact, you could come here and say, let me come here and say x underscore train dot columns. So columns are total bill, sex, smoker, day, and time. So what we can do is we can actually have a function in the def make prediction. This is just to show you this. Normally, a step like this is what you want to learn when we get to model deployment. But I just want to show you that the model now we now have something to predict a tip from somebody that we have never seen before that is just coming into our establishment. So we can say def make prediction, and the prediction that we're going to be making is going to be star star quags, right? So or star star columns, right? So you should already by now know how unlimited keyword argument works. But let me just show you this. I say return columns like this, and I call make prediction like this of. So I can actually say total bill. Or should we just pass it? Let's always pass in our to save time. Let's always pass this in as a dictionary. That is going to save us a ton of time so that we finish early. So let me just come to this place, and columns is going to be a dictionary, and it's going to be a dictionary of the data, or let's call it new data, new underscore data. So here we can do values equals let's say a new person comes in, I'm just going to grab all of this here, put it here, and say total bill of the person is, let's say the total bill of the person is 35.4. Their sex is uh male. Let's go check how sex is written in the main data set. It's capital M. Everything starts with capital. So that's going to be male. And let's take that to the next line. Smoker is, let's say this person smokes. Smoker is yes. Day is sun, sun. Time is dinner. Let's take this to the next line too. Then size of their table is, let's say, 3. And we end that. So I'm coming, but I should say return new data for now. And I come here, let me remove this. And I come here and I pass in values. That is what we are trying to do. So you are going to get out this particular dictionary. So it comes in normally. Now, the other thing, in fact, let me take this to the next line, Control X, so that we have some clarity in the way we are doing this. I'm going to say make prediction on new data. Then I'm going to paste that here. Great. So what we now want to do is, if you've ever tried to create um, a, a data frame from a, a dictionary, you have to make this into a list. These values here, they have to be a list. So what does that mean? That's going to be new underscore data equals. So we are going to use a dictionary comprehension. So we are going to say key, then values inside a list for key, comma, values in new underscore data dot items. So let's say value like that. Then now, if we run this, let me just run this and show it to you. Then run this. So this is already going to be list. Can you see something pointing to a list like this? So this is what we can convert to a pandas data frame. So I'm going to say new underscore data is going to be equals to pd dot data frame, and that is going to be new underscore data. So again, if I should run this and run this, we now get the data frame unless if there's an error. So we have a data frame now. So we've passed the information that we accept from the user has been turned into a data frame, which looks like the exact thing that we got from the main data. So what we have to do is here, it is looking like the original data. Sorry, dinner should be just dinner like this. So what we now want to do is we want to make sure that it looks exactly like this, because we must encode. Computers don't understand words like we established earlier. And what did we use to fix that? We fixed that by doing encoding. So where's encoding? This place here. But we already have the encoder object. So we don't need to do it again. We just need to transform it. So what are we going to do? We are going to come here and say, we're going to say new underscore data of, actually we must do, uh, we have to loop over the label encoder. So this is what I mean. If you come here, let me put it below here. If we come here and check label underscore encoders, you're going to see that each of those columns have their own associated encoder. So we are just going to loop over this particular place and get the associated encoder. So I'm going to come here and say for column in label underscore encoders, you could call dot keys if you want. But normally, if you look through a dictionary, it is actually going to be the keys that you are looping over without, if you don't put dot items. So we say data of column is going to be equals to label underscore encoders of that column dot transform data of that column. So basically, if we call label encoders of sex, for example, which is what we are doing here, if I should say label encoders of sex and I run this, it should be in quotes, not a variable, should be a string. So it's going to return the, can you see, the encoder object associated with sex, which is what we are also getting here. So label encoder of sex, transform sex, something like that. So if we run this now and cool, and we check it now. So each of these things are going to be 0, 1, 2. We have an error. What's the error? It says y contains previously unseen labels 0. Let's check. Let us check for which one is that. It's probably going to be for. Let's firstly check um each of these guys here. Are they all capital? Yeah, Dina, son, no, female. Okay, that. Let's go check. We have what now? Dina, son. What's the issue? What's the issue? What's the issue? Okay, let me do this first. Let me take contains what previously unseen labels. For which one? Uh, okay, let's check for each one of them. So I'm going to come here and say, instead of doing this, I'm going to remove this for loop, Control X, then come to the top here and say all of the mention of this. I'm going to change it to sex. We are going to try it out one after the other. Sex like that. So let's run that and run this. If sex worked, sex did not work. Let's try for day. Let's try for smoker. Control Z, 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 Z. I can highlight this. So let's try for smoker and see. Smoker. It is going to be some little error that is probably very stupid. Okay, so something Y contains is doing that for every single one. Hold on, please. Total bill, sex, smoker. Wow, what's happening? Again, let's come to this place and say label encoders dot transform. So let me actually remove this line, run this, like run this line, run this line too. We should have our data frame. Okay, so let's save it as new underscore data first and save that. So if I should say new underscore data of sex, let's see if it encodes it. It encodes it. So what's happening? Let's go check. Let's check for smoker. Smoker. It's working. So let's just copy this place. Control X. Paste it here. Control V. Label encoder smoker transform new data smoker. So let's run that and run this. So it should fix only smoker alone. Again, we have that particular error. Length of one does not match length of index. Okay, that's a different error. And what error is that? Oh, right, perfect. This should not be new data. And this should not be data, it should be new data. Okay, it's just here. Not even across board, it's just here. New data. So if we run this, sorry, again, we have new data. Yeah, let's see. I mean, I could have just stopped this video, paused this video, and okay, it encoded for smoker now. Encoded for smoker. So smoker should be in zeros and ones now. I don't know why that. Okay, so can you see? Smoker is one now, and what we actually want to now do is get back into our for loop. So we're going to say for column in. We can actually use the categorical codes that we created at the top earlier. We can use that. Just thinking, yeah, we can use that. So we can do this for column in categorical columns. We can tab this in and say new data of column. So Control D of column. Great. So let's run this and run this. Perfect, it worked. So run this now and we should have perfect. All of this is done. So it's correctly encoded. So we just need to come here now and make predictions. We just come here and say predicted tip is going to be equals to model.predict. And what are we trying to predict? We are trying to predict new data. And here we return predicted tip. Perfect. So we should run this now and run this and run this. So we get this is the tips that is associated with this person. So let's just return the first thing in the array. So it says this person is expected to tip 4.24. So let's change this one to maybe 65.4. Male smoker, yes, came in on a Saturday. For dinner, table size is 4. Let's see how that impacts the new. So we should run this. Can you see? So we are now predicting different charges based on the new model that we have trained to perform that. And that's the whole idea of machine learning. And we can deploy this and all of that. And this is all of the idea behind, this is some of the ideas behind majority of the algorithms that we interact with on a day-to-day. And that's what we are going to be covering um, in this particular playlist. So it's exciting. Data science and machine learning is exciting, and I cannot wait for you to actually experience the cool stuff that you can do. So that is that. I'm going to catch you in the next one, which is going to be a class on logistic regression and also um, classification algorithms. So thank you. See you in the next one.